Hello, Brunky here. We're back and we're going to talk about system engineering, what this is. I have this toy here. It's made of plastic. Obviously, at some point, some chemical or materials engineer had to go through and select all these different types of material that this device is made out of. Then you get down into the actual mechanical components of these guys. Somebody had to assemble this together or define how this part got assembled together, and then need a little bit of structural support. And then you get into the electrical aspect. You have circuit boards on here that drive these devices backwards and forward. You have a circuit on here. You have a circuit on here. Then you get into the RF arena where these bad boys need to communicate with each other wirelessly in order for these to function properly. And then you have software. Software has to go through and program these successfully in order for them to move. So when you push this button on here, it causes a reaction here. So who is ultimately responsible for ensuring that these devices here function in accordance to how they're supposed to? This is where system engineering comes in. They define all the requirements for the system in order for them to function. Well, let's start by actually defining what is a system. So I took this definition from the U.S. Department of Defense System Engineering Fundamentals. So a system is an integrated composite of people, products, and processes that provide a capability to satisfy a stated need or objective. I can't talk. Now we have a subsystem, which is a grouped function or domains which make up a system. Now, the actual discipline of system engineering can be broken into two different domains. You have a technical domain, and you have a managerial domain. Technical domain focuses on the design and integration of these complex systems, and the managerial domain focuses on management aspect of these over their lifetime. System engineering was formally recognized as a discipline in 1950s, but it's been around a long time. You can say that there was some form of system engineering in your first human construction project. Somebody had to put a plan together and fulfill a need for somebody else when they built the first house. This looks more like an art than it does an actual engineering discipline. So there's a lot of engineering that actually goes into it, but there's a lot of art and a lot of subjectivity that also goes along with it. I mean, half the stuff that system engineers do is draw things, believe it or not. This is how you can have totally different implementations that do the same thing. You know, you have two different trucks. You have your Chevy, you have your Dodge. Both of them fulfill the same exact need, but the implementation between those are different. So it came down to World War II that saw the need to implement a disciplinary action that actually formed up the system engineering process. So you had a chief engineer that was responsible for an entire product. So he couldn't oversee the development of that entire product by himself. So he had subjugates that had been assigned to a specific domain to deliver that product. And so that's where the need actually arises to make this a formal discipline within engineering. Here we got that example of the RC car yet again. So we can break the subsystem down into two separate units. We have the transmitter unit and the receiver unit. On the transmitter unit, we have this power delivery and storage subsystem, an RF transmitter, a human interface, as well as a protective housing. On this receiver unit, we can subdivide this up into a power storage and delivery system, RF receiver, a protective housing, powertrain, and we can even assign subsystems to those like a powertrain control. Keep in mind all this stuff is subjective and it might change depending on the person or organization that's doing the system engineering. When does the system engineering process start? It starts as soon as you receive the customer requirements. That's when that starts to kick off. Or in the case of entrepreneurship, you might not have a customer requirement. You might be sitting there and be like, I want to do this. I think there's a customer out here for this. So let's do it. Hi, girl. Well, you're going to get these requirements from the customer. They might be clear as day. There might be a lot missing. You never know. It's going to be a mix of things. How do the system engineers gather requirements? They build a concept of operations diagram. Everything that you think it's going to do, review it with the customer, and they approve or not approve, and you get it wrong and you have to reiterate. Thing about system engineering, it's a constant reiteration process that you have to go over and over and over again. Next, we have what's called a design reference mission. It's to simulate a mission of the device with the intent of use. Let's say you design an RC car, you want to move it forward, backwards. You design it and you'd be like, hey, we made this go on grass. What about sand? Let's try it on sand. So that would be like a design reference. Another tool that they do is what is called a system breakdown. So we already went through a system breakdown with the RC card. Next is your operational environment. That entails everything you'll have to interact with your device that you're creating. Give a car, for example. A good operation environment for that is your road. You drive on the road, so you have to design for the driving on the road, obviously. So you know you're going to need tires, you're going to have some traction that you need to take care of. And then you also have a fuel. So does it make sense to design your car off of pixie dust? No. Gasoline, where are they going to get the gasoline? Well, there's gas stations everywhere. That's usually not a problem. What if you wanted to use a different source of fuel like hydrogen? Well, they're going to have to get that some way, somewhere. And that's going to affect how you design your product. And finally, you have a use case diagram. Picture, and you encompass everybody that interacts and is involved with that product, from the customer, from the distributor, marketing, from the engineering team, everybody that's involved. And you break down, what are the use cases for this specific feature. Next, you have what's called a functional diagram. And that breaks it down into individual functions, which allows you to write additional requirements. All these tools combined are the realization and for the writing of requirements. This assists and covers all your bases for that. And it's an iteration process where you have to go through it over and over and over again until you get what you think you need. And that's when you hand it down to the design engineers. So your requirements are done when the design engineers can take those requirements and design hardware, design software, design a mechanical structure, design the system within it, and it allows the interactions between those. There's far more diagrams and tools that system engineers to use to analyze, build up, and design their systems. I think of one other one. When you go through and you see that space launch and it blows up in the middle of the flight, how do they figure out what exactly went wrong? You have a fishbone diagram. You analyze your system and you go through you go through your functional domains first. Determine, can this functional domain cause this? Can this functional domain cause this? And then you step down and you go from there. And then you actually end up to where where that failure is after you go through iterations and iterations of that diagram and understand what can cause the failure, and then you're working backwards from there. And there's also other tools, and these tools aren't limited to just system engineering. Business. So I was going through business school at the same time I was going through system engineering. And there's a whole lot of overlap between the two where they get used between system engineering and business. And it was like a double whammy. I learned both at the same time. Go figure. As far as system engineering is concerned, every industry is different. And they do things every so slightly in between all of them. You're going to have fluctuations between those. So you have certain industries that are going to require you to get a master's degree after you get your engineering degree. There's others that you get a certificate from, and it's mandatory by the organization that you go through and get it. So it all depends on what industry and what job you're working at. Now, from my experience, a lot of the different organizations go with a specific model of breaking it down to electrical subsystems, mechanical subsystems, so that domain holder that defines the requirements for the electrical systems are electrical. Not everybody does that, and the system engineers have to know the mechanical, electrical, and all the different domains. If you define your requirements right, it shouldn't be much of an issue. So some of the reading I would suggest is this ISO standard. It's got some pretty good information, some pretty good tools that you can use in there. You have this NASA System Engineering Handbook that walks you through NASA's whole entire process. And then you have the system engineering and principles that most people get when they're in school. There's a whole entire V model that I haven't even covered. So this is just the up to requirements capture. After requirements capture, that's when you adopt those requirements. You build your system, or you build the smaller subsystems, components. You test those components. You verify the subsystem. You verify the system, and then you execute, and you do an iteration process of continue to maintain that system as it goes through its life cycle. So there's a lot to cover. I only got to touch a hair, but if you enjoyed this video, hit the like. If you enjoy this content, subscribe. You have a wonderful day.